Hi, what if you wanted to design a better multimeter? Not one in terms of features, but one in terms of lower burden voltage. Now, I've mentioned burden voltage before. I've even designed a product to overcome burden voltage limitations on a multimeter. It's the microcurrent. You've seen many times I've mentioned it and had it in many videos. I've even written a whole article on the project and burden voltage and what it is and how it's a problem. So click here or down below or somewhere to check that one out. So I thought we'd take a look at a typical multimeter current measurement front end and see if we can actually redesign it so that we get improved burden voltage performance. There could be a few traps in this, may not be as easy as you think. So let's go. So what I've got here is actually a typical multimeter front end for the current measurement inputs. So we've got our milliamps and microamps shared jack. That's fairly typical for a multimeter. Probably the majority out there have them shared, and then they have a separate amps jack as well. And of course the ground jack here. We're not worried about the positive voltage input for voltage and resistance and all the other measurements. That's actually an entirely separate circuit effectively. They might even have like a big isolation slot on the PC, physical isolation slot on the PCB itself to actually separate the two sections. So we're not interested in any of that, just the current measurement capability, because that's where burden voltage is a problem. Just a quick recap, burden voltage is the voltage dropped across your multimeter, across the terminals of your multimeter when you measure current, and it's to do with these internal current shunt resistors that are used. They're resistors, so when you pass current through them, they drop voltage. And in many cases, this can be a very significant voltage. It could be in the order of hundreds of millivolts or even several volts drop. And if you're trying to measure the current in, say, a 3.3 volt circuit, and your multimeter is actually dropping a volt or even half a volt, that can cause real big problems in your circuit. So that's why we want to minimize it. So a typical multimeter front end looks exactly like this. And we've got our amps jack here. It goes through the HRC fuse, 10 or 11 or 15 amps sometimes. High rupture capacity fuse designed to fail really safe with high surge overloads. And they're typically rated at 1,000 volts because otherwise if they're too low a voltage, some of the cheap multimeters, they might be HRC fuses, but they might not be rated 1,000 volts. It might be 250 volts or something like that. So they're not nearly as safe as the 1,000 volt ones which are designed to stop arc over and stuff like that. Anyway, that goes in. It goes into a current shunt resistor here. In this case, it's 10 milliohms or 0R01. If you haven't seen that terminology before, I could have written this as 0.01 ohms like that, but it's typical to replace the decimal point with the R like that. It's just common terminology. You don't need to be confused, just understand it. So that's what we're going to use here. So 10 milliohms current shunt resistor. For the amps range, almost every multimeter out there is going to use a 10 milliohm shunt. And you've seen these if you open up a multimeter, that it's typically like a little bent wire. That's like nichrome or some other low temperature coefficient metal that they use to form the current shunt. There's a few multimeters, real high priced, high quality ones on the market that might use a proper SMD current shunt, for example, a 4-terminal one, but most multimeters on the market just use a nichrome resistance wire because A, they're very high power, B, they're cheap, and they just do the job. Now, of course, you've got to sense the voltage on that. So that's why I've shown these two sense terminals. That's a 4-wire sense terminal measurement, and I won't go over that, why I've done that in separate videos, I'm sure, but because it's such a low value resistance, 10 milliohms, all of your PCB trace resistance can cause a problem. So if you're not sensing the voltage directly across the current shunt terminal, then it can cause issues. Yes, you can software calibrate that out of with your multimeter calibration, but typically the copper on your PCB is a different temperature coefficient to your current shunt resistor, and it can get all messy and changes with temperature and stuff like that. So you really need to sense that properly, and a well-designed multimeter will do just that. Now your milliamp and microamp jack, typically shared up here, gets a little bit more complicated. It does go through a fuse just like down here, but a lower rated one. Once again, it's higher rupture capacity, HRC, but a lower value, typically like 600 milliamps, for example, for a 500 milliamp maximum current range. Once again, 1,000 volts for that arc over protection. And then generally they're going to have a diode bridge to actually clamp that voltage across the current shunt resistor, and they'll typically have that directly here. So you've no doubt seen diode bridges before, and this is a typical surface mount package, might be the DF10S for example, and these are going to be rated at 1000 volts. Now they don't always use a diode bridge like this. You might open up your multimeter, you might find that they're using 4 or sometimes 5 or 6 diodes in various configurations, usually a bridge configuration, to actually clamp the voltage across to protect your current shunt resistors inside. Because if you accidentally use your multimeter incorrectly and put a voltage across here, then it's going to be presented straight across the current shunt resistor, and that could blow the arse out of the current shunt resistor. So you want to clamp the voltage. The reason they use a diode bridge like this is just to give a slightly higher voltage. I won't go into the details, you'd have to go into the parametric curves and all that sort of stuff, but it kind of matters down on the microamp range and things like that. So they've basically got 2 diodes in series and then back to actually protect it. So it might be, say, a 2 volt clamp-in protection across your current shunt resistor. So I'll just leave that to you to figure out what, say, 2 volts across, you know, a 100 ohm current shunt or a 1 ohm current shunt, how much power can be dissipated in there, and hence why you don't want to blow up your current shunt resistor. It's just some protection. So it's just protecting your resistor just long enough for the fuse to blow. Now after the fuse, it's going to go into this weird looking thing here. I've actually tried to draw a range switch, and the range switch is that switch on the front of the multimeter. And if you're taking a multimeter apart, you've seen one of my teardowns, or go do it yourself right now, you'll see that there's little contacts, wiper contacts on these range switches, and there's traces on the PCB. So I've just sort of, you know, simulated that. I've got 2 different positions here basically, and the red just shows the short-in bar there for the microamp range, or there for the milliamp range. So it's just a switch basically, single pole, double throw. So on the microamp range, it goes straight into a 100 ohm current shunt resistor. Easy. That's a very, very typical value you'll find on probably most multimeters. Very close to that sort of value for your microamp range. And then if you switch to the milliamp range, well, it disconnects this 100 ohm resistor and then goes down here, and we've now got a 1 ohm current shunt resistor, and that's actually in series with the 10 milliohm current shunt resistor down here. And sometimes they might actually put in not 1 ohm, but they'll actually put in 0.99 ohms like that, or 0R99 if we want to keep that terminology, so that when you put it in series with the 10 milliohms down here, it equals 1 ohm total. So it's actually using both of those as the current shunt resistor effectively. And the reason they do that, engineers just like nice round numbers. It comes out nice. You can, it didn't matter if you did that and had 1 ohm plus 10 milliohms down here. You could calibrate it out in software. It's no problem. Now, unlike for the 10 milliohm shunt resistor down here, this one up here, I've only shown 1 wire going off because you don't really have to 4-terminal measure that. You don't really have to do it because the PCB trace resistance is a tiny, tiny fraction of that 100 ohms out up here. It's going to matter for this 1 ohm one because you're getting down there. So typically they might take a sense point there on that 1 ohm resistor and actually the other sense point down here. So they're actually using both of those as the current sense resistor. But they are typical values that you'll find in probably the vast majority of multimeters out there. 100 ohms, 1 ohm, and 10 milliohms. So now let's take a look at this table down here and see what our burden voltage is for the different ranges. A typical multimeter, I'm taking the case of a 50,000 count multimeter or a 5,000 count multimeter. So it'll have a 500 microamp range, 5,000 microamps or 5 milliamps. It's actually microamps as we'll see, but it could be displayed as 5 milliamps. Then 50 milliamps, 500, 5 amps, and then 10 amps down here. 10 amps is limited by the power in the current shunt resistor and other stuff. Sometimes they can go up to 20 amps peak for 20 seconds or something like that. Then you've got to let them cool down. Otherwise, the current shunt heats up too much. Anyway, so these are the different shunts that are used. So in the microamp range, both 500 microamps and 5,000 microamps, they switch in the 100 ohm shunt resistor here. And in the 50 milliamp and 500 milliamp ranges, then they switch in, you can put it down to the milliamp setting. You switch your range switch to the milliamps, goes down here, and then you're using your 1 ohm current shunt resistor. And then when you specify amps, you've got to physically move, not only, well, put your switch to the amps milliamps position and then move your probe down to here. And of course, it's using the 10 milliohm resistor down here for the 5 amp and 10 amp ranges. And then if you just use Ohm's law, 500 microamps times 100 ohms here, then that's 50 millivolts, or what's called 50 millivolts full scale, or sometimes you read the data sheet for a multimeter, it might say the burden voltage is 50 millivolts max, or something like that. They might use a max figure. It's the same as I'm just using full scale there. So that is a typical figure, and then once you go up, of course, we're using the same current shunt resistor here for both of these ranges. So, but because this one goes up to 5,000 microamps, you've got to multiply 5,000 microamps, maximum figure, maximum current you can measure on that range, by the 100 ohms, bingo, you get 500 millivolts full scale. So, as you can see, we've got the same current shunt resistor being shared between two different ranges, and we get two different burden voltages here. 50 millivolts, that's not really a big deal. You know, like, you wouldn't really worry about that. You'd be pretty darn happy if your multimeter had 50 millivolts burden voltage on every range. That'd be a kick-ass multimeter, let me tell you. But 500 millivolts, that's half a volt. So if you're measuring a 3.3 volt rail, the current on the 3.3 volt rail, it's dropping it down to 2.8 by the time it actually gets to your chip and your circuitry. That can cause a lot of problems. So that's a real issue. That's really quite high. And then you can just go do the same math here. 50 milliamps times 1 ohm is 50 millivolts, and it's the same order like this. So 500 milliamps times 1 ohm, 500 millivolts again. So we've got these sets of ranges like this based on our current shunt resistor, and the amps one down here, 50 millivolts and 100 millivolts. So you can see that there's a couple of ranges in there that are really troublesome, the 5,000 microamp and the 500 milliamp. We really want to fix those. And just to be complete, burden voltage is often, in fact, probably more correctly specified in volts per amps. So I've just calculated the volts per amps figure, and you can go through and double check that. Anyway, we'll work with the full scale burden voltage here. But what that burden voltage here does tell you is it allows you to calculate if you're on the 500 microamp range and you're only measuring 100 microamps, then we're 0.1 millivolts per microamp. So the 100 microamps will give us a 10 millivolt drop on there. And of course that's obvious because it's 50 millivolts full scale. We're 1/5 of that, 10 millivolts. But that's the thing, Murphy will get you every time. I guarantee that your project you're trying to measure will want to take like 490 milliamps or something like that. So you'll have to go, if you want the most resolution on your multimeter, which you do, you'd go to the 500 milliamp range, but then you're going to get a 490 millivolt burden voltage drop. It's terrible. Now there's actually a couple of ways to overcome burden voltage with just your regular multimeter. You can A, switch up a range, so if you're measuring that 490 milliamps, you can switch up to the 5 amp range, and you're going to be dropping bugger all. What are you going to be dropping there? Like, you know, 5 millivolts, right? Bugger all. But you lose resolution on your multimeter, so it's a trade-off. The other way to do it is to hook your project up to a power supply and tweak that power supply to compensate for the drop on your multimeter, the burden voltage. But then if your product is changing currents all the time, no, that's not necessarily a good thing to do. But as many of you may have already guessed, these figures aren't right. It's a bunch of theoretical BS. Why? Because we've only taken into account the actual shunt resistor value in here. We haven't taken into account all the other stuff which is in here. And well, what other stuff? You might be saying, well, we've got some contact resistance here on the switch, but that's not going to be much, right? It's going to be milliohms. It's going to be, you know, nothing, right? Really, compared to 1 ohm and 100 ohms, don't even worry about it. But we've got a fuse, and we've got a fuse here as well. But you might be thinking, well, fuses are just a bit of wire, right? That melts. It's a short circuit. These HRC fuses, and in particular the high voltage ones, the 1000 volt ones you want to use for safety and that are specified into your high quality multimeters, they actually have quite a high resistance in them. And we'll take a look at the data sheet and we'll measure a couple of these typical fuses, and you'll see that the fuse resistance can actually be higher than your current shunt resistor in here. You might be using a 1 ohm current shunt resistor for your milliamp ranges here, but your fuse might be 1 ohms or even 2 or more ohms So it's higher, it dominates your voltage. So our 500 millivolts burden voltage that we thought was fairly bad down here, it can easily be double that. In fact, you can almost, on a good quality multimeter, with that value shunt resistor, you can guarantee that it's going to be double that, pretty much. So I'll just measure some real fuses here. They're cold DC resistance at room temperature, and let's actually see what they are. First, we'll actually null this out. I like using my LCR meter for this because it goes down to 100 microohms resolution. Very nice. So this is this, a top, really good quality ASTM HV620, 600 milliamps, 1000 volt one. Okay, so this is a 1000 volt fuse you'd typically find in a multimeter. There we go. You do get around about that 1 ohm figure. Let's try another one. Seba, another top brand, 400 milliamp one. This one's a bit lower. Once again, it's 1000 volt rated on there. And what does this one measure? Look at that, 1.3. Yeah, that might be because it's a bit lower in current, but it's that order of things. And hey, let's take a look at this big Seba one. Look at this big ass thing, 440 milliamps. You might think, oh, this is going to be really low, right? This is a multimeter fuse. Wah, 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 wah. Look at that. 1 ohm once again. Unbelievable. And this busman fuse, the ones that I think Fluke specify these ones. So it's 440 milliamps again. And that one's better, 0.66 volts. Is that... I don't know if that's 1000 volt. Is that 1000 volt? Yes, it is 1000 volt rated. So that one's not too shabby. And look, here's another bus fuse. This is a 1 amp one, okay? So you'd think this would be really low because it's 1 amp. No siree, Bob. That's still 0.55 ohms. That's very significant. And here's an 11 amp one. So this is typically on the 10 amp range. So once again, quality one, Seba, 1000 volts. Excellent. And there you go, that's around that 10 milliohm figure that we were talking about. And once again, here's a Fluke, here's a little fuse designed for FLU, so they're designed for use in the Flukes. Once again, that one's going to be around that 10 milliohm figure as well. Now, I'm not sure if you can see that, but this is actually a 500 milliamp fuse. I've got two different 500 milliamp, just M205, crappy one hung low brand glass fuse. In fact, this one's not. I'll show you. This one is though. This is just an absolute cheapie, right? So this is 500 milliamps, okay? And let's have a look at what this one is. Look at that. Look at that, less than 100 milliohms, 93 milliohms for half an amp. So these crap little glass fuses, which you should never use in multimeters if you're doing anything serious at all. And, these top quality 1000 volt rated ones are like 10 times larger resistance. That's just we're into material science now. So if anyone knows, I don't really know what causes that. It's the material inside and construction. I don't know. If anyone's actually got any real proper detailed info from the manufacturers on what's causing them to be this high, but the fact is they are. And then we've got this one here, which is got a little ceramic former in there. It's a fast blow 500 milliamp fuse, yet again, only 250 volt rated. Okay, and that one, this is not a no-namer. It's got all the requisite standards and stuff like that, but it's, 0.3 ohms, so still 1/3 of the resistance of a proper one at a similar sort of rating. And you're going to see a similar thing on the amps range here with the 11 amp HRC fuse. It's about 10 milliohms or thereabouts, about the same as the shunt. But typically on your amps ranges, you're measuring bigger system things, usually probably at a higher input voltage like 12 volts or something like that going into your product. You're not generally measuring low logic rail, low voltage rail stuff. So burden voltage is typically never really an issue on the amps range. It's not really a problem that needs solving, but certainly on the milliamps and the microamp ranges here, these two ones in particular, we really need to fix those. So let's take a look, but may not be as easy as you think. Otherwise, every manufacturer would fix it, but they don't. So how do we fix this burden voltage problem? Well, it might seem easy. Just like my microcurrent, I use very low value shunt resistors and I use a times 100 amplifier. Times 100 amplifier is a little bit tricky, offset noise and stuff starts to be a problem. But hey, we could say drop this 100 ohm one, especially for this range here, 5,000 microamps, we can drop that by an order of magnitude, i.e. 10 times, down to 10 ohms, and then we can feed that into a times 10 amplifier, which shouldn't be too much of a bother, and Bob's your uncle. We've fixed the burden voltage on the 5,000 microamp or 5 milliamp range here. And likewise, we could change this 1 ohm one for the milliamps, we can change that down to 0R1 or 0.1 ohms, and then once again, we take that out and we put that into a times 10 amp, and bingo. And like I said, we don't really have to worry about the amps range, so we're not going to bother fixing that, but surely that's all we have to do. And we've fixed our burden voltage problem. But, you remember the fuse. We might have dropped this by an order of magnitude, right? A nice 0.1 ohms. Oh yeah, that'll drop our 500 millivolts full scale down to 50 millivolts. Yeah, for the shunt resistor, but you still got 1 ohm in your fuse up here. So it's still going to be in this order of 500 millivolts. Sure, you've made an improvement. You've like halved it. It used to be a volt because of the 1 ohm plus the 1 ohm in the fuse. So that was, you've halved it, but that's, it's almost not worthy of your, the cost of implementing your nice, fairly reasonable cost times 10 low offset chopper amplifier in there, like a Max 4238, like I use in the microcurrent. It's almost not worthy of the cost for that. So really, we can't just do that. We have to do something with the configuration here to fix this, because this fuse is a real pain in the ass, and we can't just get rid of it, because the fuse is all part of the safety ratings, the UL testing and the CAT standards and all that sort of jazz. We can't just take it out willy-nilly just to get that, although you can temporarily take it out and do that, and you can lower your burden voltage of your multimeter, but that's not what we're talking about here. We're trying to fix it from a design standpoint. Now, some people might mention poly switches. You just whack a poly switch in there and she'll be right. Well, it's not the same thing. You don't have the same high rupture protection, the arc over and everything else. There's a reason that these high rupture capacity fuses are used in multimeters, and we want to stick with it. Now, there's several ways you can approach skinning this cat. And, well, one of the first things that might come to mind is, well, and you might have actually seen on some multimeters, instead of having milliamps here, let's have a combined milliamps and amps jack here, and then take this out to our amplifier, which can be times 10 and times 100, for example. So now we can actually go through with this would be 0R01 and 0R01. Let's go through and actually do the calculations again to see if we can actually do this with the times 10 and times 100 amplifier. So the burden voltage is now, well, this remains the same. 5 amp ranges was 50 millivolts before. It's still 50 millivolts because nothing's changed. But now we've got the milliamps with our 10 milliohm current shunt resistor here. So it was 500 millivolts full scale before. Now it's 5 millivolts full scale. And for the 50 milliamp range here, well, it was, so 50 milliamps times 0.01 ohms is 500 microvolts full scale. And well, that might sound okay, 500 microvolts full scale drop across here, just whack a times 100 amplifier in, and Bob's your uncle, right? Well, no. Let's take a look at the data sheet for the Max 4238/4239 that I use in microcurrent. It's one of the best low offset, almost zero offset chopper amplifiers on the market. And it's got a typical, in quote marks, offset voltage of 0.1 microvolts. And you, of course, have to multiply that by the gain here. And if you have a look at the microcurrent here, you can see it is very typically around about that 0.1 volt typical figure on the data sheet here at room temperature. And I've got it actually, the input shorted there like that, but we could have it on the actual range itself. There you go, it's on the 10 milliohm current shunt resistor there. And you'll notice that it is 0.01 millivolts, or can get that high. It drifts a bit with temperature and stuff like that. But the typical figure, yeah, it's 10, let's take it as, say, 10 micro volts on here, but because this has got a times 100 amplifier on it, you've got to divide that by 100, and that's the input offset voltage, and it is around about that typical figure you find in the data sheet. But hey, the maximum figure, if you're really going to town, the maximum figure could be up to 2 microvolts. But hey, that's over the entire full temperature range and worst case process characteristic and everything else. But I've manufactured thousands of these, and each one's individually tested, and it really is that low. And that sounds pretty low, but hey, let's take a look at the resolution. If we've got a 5,000 count multimeter, we might get away with this. But, you know, we're designing a reasonable multimeter here. Let's say it's 50,000 count, 4.5 digit class multimeter. What's the resolution? What's that least significant digit on the display representing in terms of a voltage at the point across the current shunt here? Well, at 50 millivolts full scale, 50, you can see that that's 50 millivolts, it's 000 after that, so it's 1 microvolt. And likewise, we just scale it down by a decade, 5 millivolts full scale, 0.1 microvolts, bingo, we've already matched the typical offset figure of our op amp. So ooh, we're starting to get a bit scared now, but now we want the 50 milliamp range, 500 microvolts full scale, with, so if that's 500, you put the decimal point there, 00, we're talking about 0.01 microvolts resolution. It's ridiculous. It's an order of magnitude better resolution than what our amplifier is actually capable of. So when you whack in your times 100 amplifier in there, that typical 0.1 microvolt offset is going to be amplified 100 times. So on your 50 milliamp range, you're going to get the couple of least significant digits just flapping around in the breeze because, well, that's just the offset voltage. Sure, you can fix it with like the null button on the multimeter, but it's going to drift a bit. It's going to change with temperature and all sorts of stuff. And really, people don't expect a multimeter, especially on the milliamp range, to be flapping around with 2 least significant digits in the breeze. So really, that is not a solution. We can't just whack in a times 100 amplifier there because the best chopper amp you can get is not going to be able to do the business. But hey, we are getting towards a solution. So that one's actually a tick. That one is probably a tick. Maybe the least significant digit might flap around by a few digits, but you know, it's probably going to be good enough. But this one is definitely out. But hey, there's probably no reason why we couldn't have the amps terminal actually do our 10 amp, our 5 amp, and our 500 milliamp ranges. Because we really are quite stuck with this 500 milliamp range. We can't use a 1 ohm current shunt resistor or a 0.1, for example, because we've got to go through this 600 milliamp fuse, which is going to be 1 ohm. So we're going to be stuck with that high 500 millivolts burden voltage. There's almost no way around it apart from implementing some sort of switching solution here that goes through our 11 amp fuse. But then we'd have to put some real beefy heavy duty MOSFETs in there or a relay to switch our 10 milliohm current shunt resistor. And there is one, like a high-end Gossen, they actually do that. They do actually MOSFET switch the 10 milliohm current shunt resistor in there, and then they can switch in. Once you've got rid of that, then you can put other resistors in parallel here. So that's why they actually only have 1 amps jack like this and can measure down to like a 100 microamp range, or I think it's 300 microamp range or something like that. Because then once you disable, if you're able to disable that current shunt resistor there, then you can put others in series real easy. Because, you know, if it's 1 ohm or something like that, you can switch it in. No problems. So that is one possible solution, just to do away completely with all this crap up here and just do it all from the 1 jack with switching. But that's not what I want to do here. I want to solve the problem for the existing jacks that we've got available. One of the reasons is that those MOSFETs or a relay or whatever, they're really big ones, they have to be big and beefy. They take up a lot of room inside a multimeter, so you've got to clear out all the space. So I'm going to propose sticking with using the amps jack and the 11 amp fuse in the 10 milliohm shunt for the 500 milliamp range. But this 50 milliamp range, hey, let's go back to the existing solution here and just use, we don't even need this this 0.1 ohm shunt here, we can get away with just our 1 ohm shunt in there because originally we only had 50 millivolts full scale drop. That's more than adequate. Even with the 1 ohm up here, it's only going to be like 100 millivolts typical full scale. So I'm reasonably happy with that. That's lowish burden voltage. It's not microcurrent low, but hey, you know, it's good enough. So I've gone and filled in a more detailed table here with the typical drop we're going to get for each of these ranges which I'm proposing here, plus the value due to the fuse up here. So the 50 milliamp range, let's use our existing 1 ohm resistor here so we don't really have to change anything. And then that gives us 50 millivolts full scale. So that gives us 50 millivolts plus, remember, another 1 ohm up here. So that gives us another 50 millivolts, 100 millivolts. We're pretty happy with that. I'm not going to quibble over 100 millivolts true system burden voltage. That's pretty good. It was really the 500 millivolts and the 1 volts that we wanted to fix. So that's an order of magnitude lower than that. Beauty. So that gives us 1 microvolt resolution. We don't need an amplifier in there. That can just go up, bugger off into the existing multimeter chipset, which has its own internal amps and stuff like that. But it expects that 50 millivolts, so it's not a problem. So we don't need any extra amplifier for that range. Now, for the 5000 microamp range, instead of having it go before, we had it going into the 100 ohm or 10 ohm resistor over here. Let's actually put that into the 1 ohm resistor. So we just have to reconfigure our range switch there. So, well, not really. We just call it milliamps. Instead of 5000 microamps, just call it 5 milliamps. So it goes through here into our 1 ohm resistor. If we do that, instead of the 500 millivolts we were getting before, bingo, we're now getting, because it's 1 ohm, 5 milliamps times 1 ohm is 5 millivolts, is it not? Plus the extra ohm up here, 10 millivolts total. Oh, beauty, right? And once again, our resolution is only 0.1 microvolts. It's in, you know, it's doable with the Maxim chip that we can actually get, and we only need that times 10 amplifier. And then this microamp range is now only used for one range, and that is now, of course, we reduce it by an order of magnitude, 10 ohms, just like we said before. So 500 microamps times 10 ohms is 5 millivolts plus 1 ohm up here, 1 ohms and 10 ohms. If something is an order of magnitude less, you just go meh. So I've just written meh in there. It doesn't, you know, it's going to be like plus, you know, 0.5 millivolts or something. Doesn't matter. Meh. So 5 millivolts system burden voltage, absolute ripper, and we just need our times 10 amp there. I think we've got a solution. So what extra circuitry do we have to add to this thing to make it work? Well, we need a couple of muxes in here, i.e. just some switches to switch the voltage across here. So we've got 3 points now. We've got one across our 10 ohm shunt resistor, one across our 1 ohm shunt resistor, and one across our 10 milliohm shunt resistor. So we can select either of those 3 inputs. It comes out here, and this is, that's a times 10 amplifier that goes into our times 10 amplifier, which amplifies that, and then we've got another mux which can select between the times 1 or the times 10 position, because we need both of those selections here for that, and that just goes to the output. And of course, yeah, this is, you remember we said down here that our sensing matters. So, you know, we'd bring our sense line there, and you have to, I won't go into details of how you would lay that out on the board, but yeah, we would have to take that as our sense terminal because that matters. Otherwise, we'd get offset issues caused by the traces and things like that. But that, I think, is our better multimeter. It's not super low, you know, burden voltage, absolutely fantastic, but hey, it's probably a good order of magnitude or thereabouts better than your typical multimeter, because some can be, like worst case, we're talking 100 millivolts here. It's not, so it's very typical down here. We haven't fixed anything with the amps range. So that's just, you know, a typical multimeter on amps. But as we said way back at the start, it's not really, for most measurement applications, it's not really a problem. I don't think I've ever encountered an issue where burden voltage has been a problem on the amps range, really. But there might be some obscure case, but we don't really need to fix that. But we're definitely fixed these 5 milliamp range and the 500 milliamp range we had problems with before. Ripper. So there you have it. This has probably been a lot longer than what I intended, but I think this is quite a neat solution. There's other ways to do it. As I said, switch in, having the one input jack and having MOSFET switch in and stuff like that is, a really nice way to do it, but it's big and complicated and expensive. So yeah, it's, but just to modify an existing type traditional meter design like this, that probably does the business. The only kind of confusing part is maybe the 500 milliamp range here would have to be marked on that jack. It'd be amps and 500 milliamps, and this would be milliamps and microamps like that, but you just annotate it on your silk screen on the front of your meter and Bob's your uncle. So there you go. Hope you got something useful out of that. If you got any better ideas, then yeah, leave it in the comments down below. Hope you enjoyed it. Catch you next time.